Welcome to this video on Automata Theory of Computation, in which we are going to solve this problem on the screen and understand most of the concepts in ATC. And so we are going to use a bottom-up approach to study this subject, in which we are going to try to solve a problem to understand the concepts. I would prefer this approach to any of the subjects you would study, and especially subjects that are logical like ATC itself. So let's start by reading this scenario that I have generated with the help of ChatGPT over here, and let's try to understand. You are tasked with designing a simple vending machine controller that accepts coins and dispenses snacks. The vending machine follows a set of rules. The machine accepts coins of 1 unit and 2 unit. A snack costs exactly 3 units. The machine dispenses a snack only when the user has inserted exactly 3 units. Otherwise, it waits for more coins. If the user tries to insert more than 3 units, the extra coins are rejected and the machine resets to start over. So basically in ATC, what we do is we are going to create a language with which the user can communicate to the machine with the help of the coins 1 unit and 2 unit in this case, and machine can respond back with dispensing a snack if the user has inserted exactly 3 units, else give back the money and not dispense the snack. So as we know, for any language we'll need symbols. Like we have ABCD in English language, we will need symbols in this scenario also. So the symbols here are 1 and 2 units as given in the question. In the scenario, the machine accepts coins of 1 unit and 2 unit. So the set of these symbols are the alphabets, and it is denoted with sigma. Next is the words. So words, or we can also call it as strings, are the combination of these symbols. In this case, it could be 1 1 1 or 1 2 2 or 1 2 1 here, 1 2 2 and so on. But the words that are accepted by the machine here are the ones that sum up to 3. For example, 1 1 1 sum ups to 3. Similarly, 1 and 2 sum ups to 3, and 2 and 1 sum ups to 3. So this is the language here. But a machine cannot understand like we humans do. It will require some system in which it can decide the word is accepted or appropriate. So we'll have to create states that define the machine at any point of time. For example, here Q0 will be a state in which the machine is given no money. That is, user has not inserted any coins. And Q1 will be a state in which user has inserted a coin of 1 unit. Similarly, Q2 will be when the machine has 2 units. And finally, Q3 will be the state in which the machine has 3 units. So we have defined the states in which the machine can be. So this states will represent in a set. So the set of the states is denoted with a capital Q, and the sets and the states are denoted with small q with subscripts that make the differences. Alright, now we are going to define the relations between these states. That is when does the machine goes from certain state to another state, and we are going to do this according to the given scenario. So according to the given scenario, machine should accept, that is consider an word or the string as appropriate only if it sums up to 3. So the machine should dispend dispend a snack only if it is in Q3 state. So Q3 will be a final state, and Q0, that is when machine has no money, will be the initial state. So the initial state would be Q0 and the final state will be Q3, and final state is represented with a set form because a language can have a lot of states that can be accepted, but initial state should be always 1. Alright, now let us start defining the relationships between the states. So suppose Q0, a machine in Q0 state gets 1 unit, then it gets transferred to Q1 or changes to Q1 state. Similarly, Q1 changes to Q2 when it gets 1 unit. Q2 changes to Q3 when it gets 1 unit. And Q0 when gets 2 units, it goes to Q2 state. Similarly, Q1 when gets 2 units goes to Q3 state. But so as you can see, this automata or this figure with states and the relationships is called automata, and this automata can deliver these 3 states, but it also delivers the states that are not in this language, or it does not satisfy the whole thing. So let's see the third point here. The machine dispenses a snack only when the user has inserted exactly 3 units, otherwise it waits for more coins. Alright, let's see fourth. If the user tries to insert more than 3 units, the extra coins are rejected. That is, suppose Q2 gets 2 units, then it exceeds 3 units, so it should reject the whole money and not suspend dispend a snack and reject all the money it has and go to Q0 state. So until here it is satisfied, but as you can see here, after dispending the snack, it should go back to the first state so that next user can use the machine. So we are going to represent this relationship with the epsilon. Epsilon is a special symbol that represents that uh, uh, to make this transition, the machine requires no input at all. So that is epsilon, and this figure is called as epsilon NFA, that is epsilon non-deterministic finite automata. So if we don't have this epsilon relation, it is called only NFA, that is non-deterministic finite automata. Now for creating a machine, it should be completely deterministic. Non-deterministic will not serve the purpose. The machine requires clear and unambiguous state, or an algorithm, unambiguous algorithm. But here, as you can see, Q3 has no way to go when it gets 1 or 2 units. So for this, what we have to do is we should convert this figure into a deterministic finite automata, that is DFA. To do that, there are several approaches. Let's see one of them. Before that, let us write the relationship in a tabular form. At the same time, we can also represent these relationship in this form also. Delta Q naught, that is the state in which the machine is in, and the input equal to the state to which it goes, that is Q1, and so on. But for now, let us do it in a tabular form. So let us write all the states here and all the possible inputs here. For now, let us fill this table. Okay, when Q1 gets 1 as input, it goes to Q0 gets 1 as input, it goes to Q1, and similarly this goes to Q2. Q1 when gets 1 unit goes to Q2. Q1 when gets 2 units goes to Q3, and Q2 when gets 1 unit goes to Q3. When it gets 2 unit, it should go to Q0, and Q3 when it gets 1 or 2 is not defined. That is what we'll have to define to make it deterministic. So this instance is denoted with a 5, that is it is not defined. And while showing the outputs for NFA here, also in the delta form, we must show in a form of set, because in NFA it is not completely defined. That is, even though a state gets a single input like 1, Q0 may go to Q1 and also may go to Q2, but in this scenario it is not so, but it can in other scenarios. So we must represent this in set form here. But in deterministic finite automata, we will be representing them as simply states. And when q0 gets a epsilon, it goes to nowhere. Though it stays in q0, we'll not write this down here. We can write it, but let it be for now. And but when q3 gets epsilon, it goes to q0. In the sense, when the q3 doesn't get, even though even though user doesn't give any coin, it should go to q0. So this is the relationship of the NFA we have created. Now let us try to convert this into a DFA. Okay, now here, why are we converting to DFA? The main objective of ATC is to find a general form of the word with which we can derive all the words possible for the language For that, we can also do it from NFA to the general form, or what we call it as regular expression. So NFA can directly be converted into a regular expression, but here let us convert it into DFA and then to a regular expression for the sake of understanding the concept. So before converting this into a DFA, we'll have to understand another concept, that is e-closure. We call it as epsilon. Okay, we call it as e-closure. So e-closure of q0 will be q0 itself. Now you would be able to guess that the e-closure is when the machine is given no input, the states the machine can reach, all the states the machine can reach is known as e-closure. So in the case of q0, it doesn't go to any other state but stay in q0. For q1 it is the same, for q2 it is same, but for q3 it stays in q3 but also it can go to q0. Now let us try to convert it to DFA. And another thing I have forgot is we should denote which is initial state and final state. Initial state with the arrow and final state with the asterisk or the star symbol, as you can see here. So we should start with the initial state, which we know is q0. So q0 will be the initial state, but before accepting q0 as initial state, we will have to check the e-closure. Suppose q3 is the initial state, we'll have to take the e-closure as the initial state in DFA. So in this scenario, the set of q0 is the initial state. We know that inputs are 1 and 2, and in DFA there is no thing as epsilon. So let's continue. So when the machine gets q0, we know that it gives q1 when it is given 1, only q1 is possible, and when it is given 2, q2. Okay, now let us take this symbol, this set of q1. Suppose the machine in state q1 is given 1, then we'll have to see the transition table for the NFA and write the same. Suppose we encounter a state with two states, or we'll address that later. Now q1 is addressed. Let's see q2. Let's take this state. So in q2 we have, for 1 as input, we have set of q3, but we cannot write the same as q3 because e-closure changes. So we will have to take the e-closure, the union of the e-closure with this. So similarly we have q0 here. The e-closure of q0 is the q0 itself. Okay, now, oh right, here we have done a mistake. This should have been q0 comma q3. Since q3 is here, we'll have to check the e-closure of q3 and write the e-closure of q3 here. Next is q0 comma q3 is the only state we have not addressed yet. q1 is addressed, q2 is addressed, q0 q3 is not addressed yet. So let's take q0 q3. We'll have to check the transition table for both q0 and q3 and take the union of them. So q1 and phi. So the e-closure of q1 is q1 itself, and e-closure of phi would be obviously the phi itself, and we'll have to take the union of both of them, that is q1 union the empty set or phi, and we get it as q1. This is how we have to deal when a state like this is encountered. So this will be q1. Similarly here we have q2 and 5. E-closure of q2 is q2 itself, so we'll have q2. So now let us check if there is any state we have not addressed. q0 q3 is addressed, q2 is addressed, q0 q3 is same as q3 q0, q0 is addressed. Okay, so we have addressed all the states. Now let us write this in a figure form, in the diagram form. Okay, so let us write down all the states that we have derived. And now, right here we'll have to decide on which is the initial state and final state. So here, as we defined it earlier, q0, the set of q0 is the initial state. But how do we find which is the final state? We do that by checking this final state, which is q3, and check which states here involve q3. It is only this state q0 q3 which involves final state q3, so this is the final state of the new derived TFA. Now the remaining task is the easiest one. we will have to just translate this transition table into the diagram. So when we get 1 to this, when we give 1 to this state, we get q1. When we give 2, we get q2. For this state, which is set of q1 is given 1, we get set of q2, and it is given 2, we get q0, q3, right? And when the set of q0 state, the state with set of q2 is given 1, it goes to q0, q3, and when it is given 2, it goes back to q0, and when q0, q3 is given 1, it goes back to q1, and again when q0, q3 is given 2, it goes to this state. Now for ease of representing these states, let us consider this state as A, B, C and D and rewrite this diagram. A, B, C, D. Have 1, we have 2, we have 1 again. 2 is defined like this, 1, and if C gets 2, it goes back to A, and if D gets 1, it goes back to B right here, and if D gets 2, it goes back to C. So now as you can see, every state is directed how to behave when it is given any valid symbol. If A is given 1 or 2, 1, it can react. Wait. Yeah. Oh, right. We have done a mistake here. If A is given 2, it goes to C, right? Right. So if A is given 1, it knows how to react. If A is given 2, it knows how to react. Similarly, as in NFA, we did not know when Q3 is given any input, that is 1 or 2, it does not know how to react. But here we know. So if the final state D here gets 1, it goes back to B, and if it gets 2, it goes back to C. Okay. So this is the DFA which we had to derive. Now let us try to derive a regular expression for this. For this we have again two ways to do it, that is cleanse formula and another is state elimination. For this video, let us solve this with state elimination method. Comment down if you want the same in cleanse, or if you want a different question to be done with the cleanse formula. We'll do it in the next video. For now, let's do it with state elimination method. Here what we do is we eliminate the intermediate states, we don't eliminate the initial state and final state, but we eliminate the intermediate states so that we can derive an expression from the initial state to final state. So what we do here is we have state A, we have state B, but we will not write state C here. We'll have final state D. We'll try to eliminate the state C but retain all the relationships here. So let's see, this relationship is taken down, and from B to D, as you can see in this diagram, it takes 2 1s. So these two are done, and now we have B to D is 2, and alright, wait, have we missed something? No. Alright, yes, no, okay, right. And let's take the next relationship, which is this one. B to D is 1, and now let's take this A to C, which costs 2 units, and further it takes to D. So A to D with it takes from C to D with 1 unit. So this relationship will have to represent it with 2 1. Okay. Similarly, for this state, we have it goes to C with 2 units, goes back to D with 1 unit. So here we have 2 1 again. And now this one, which is C to A, which costs 2 unit. So from D to C is 2, and C to A is again 2. So this takes 2 2. Alright, have we missed any of the relationships out here? Okay, now let us try to eliminate the state B. Let us take state A and state B as final states. Oh, right, we have another relationship here. It goes from A, costs 2, comes back to A, again costs 2. So we have a loop here, just like D to C and C to D costs 2 1. Here goes to A to C and comes back C to A, costs 2 2. Alright, so now there was another one. Is it? Yeah. Right, there's another one. Yes, there's another one here. So we also have B to C and again C to A, which is 1 2. Okay, now we can eliminate the state B. For that, let's do the same way. A to D we can have through B, which is triple 1, and now we have A to B. Okay, let's take this one first. We have A to A itself 2 2, and we'll take this one. D to D itself is 2 1. Now the direct, let's write all the direct relations first. This is 2 1. So for this we can write like this, that is plus operator means that triple 1 or 2 1 here, and similarly a dot operator will represent that both the elements concatenated. For example, if we write 1 1 1 dot 2 1, it means 1 1 1 2 1 is a valid string. And how do we represent this loop in the form of an expression? That is represented with a star as a superscript. That means it can have that is 2 1 can be repeated any number of times. Suppose 2 1 is given a superscript of 2, that means 2 1 should be repeated only twice, and so on. Alright, now let's just come back to this. Now we have triple 1 plus 2 1 here, and that goes back is to 2. Okay, let's take the next relationship, which is this one. B alright, B to D will be 2, and we have A to B as 1. So A to D will be also 1 2, and again this one D to B is 1, and again it goes back to D with 1 1, so it is 1 1 1 over here, because this is a loop here. Next is this relationship. This relationship is again a loop. When we eliminate the state B, it goes from the state A to B with 1 unit and goes back to A with 1 2. So this will be 1 1 2. Okay, so we have tried to translate all the relationships here. Now this is the state we had to come to finally convert it into a regular expression or the general form of the language. From this state we can convert it into a regular expression with general intuition as well, but we have a formula for this, which is R plus S U star T dot S U star. So here this RSTU is, this is S, this is R, this is, okay, so this is S, this is T, this is U. Alright, so the final thing we'll have to do is substitute this. So it is 22 plus 112 plus S is 111 plus 21 plus 12, and we have U as 2 2 with a star. We have T as 21 plus 111. Yeah, I just forgot a star here, asterisk, and next term with a star. Let me just drag this. No, space will be not enough, so I'll just continue here with a dot, which means we'll have to concatenate these two expressions, the first expression and this expression. So S is 111 plus 21 plus 12, and U is okay, we have assumed it wrong. Alright, so this is R, but this is T here, and this is U. Okay, now let us write this expression properly. S is 111 plus 21 plus 12, and U is 21 plus 111 star, and T is 22. This will have a whole star, and again we'll have S plus 2 1 plus 1 2, and again u is 2 1 plus 1 1 1 whole star. This means that the machine will start from here, and it can start with the state A, and it can loop infinite times though, but it can also at the same time go to D and come back to A again, and in that it can go from A to D and have some loops there with U, and come back to A with T, and finally it can go from A to D and iterate U several times and stop. And this star over here can also have 0 as its value, or can have infinite in any number. So this will be the regular expression for this scenario. Thanks for watching. Please subscribe this channel and comment down if you have any suggestions and if you have any doubts, and or if you want any questions to be solved, you can comment down the question, and see you in the next video.